anyone have any homework questions you'd like me to go over, explain anything like that? Okay, we've been doing circular motion. So now we're going to get into the next topic. And that is conservation laws. And there are two of these. And now as we start to, as we get into the last few topics in this class, it's going to start to be, basically we haven't done that many topics so far. We've done kinematics, we've done kinetics. There aren't too many directions you can go on problems, If you have forces in the problem, you need to go do the kinetic stuff. If you don't have forces in the problem, you do the kinematic stuff. That's really all there is. But now there's going to start to be different ways to approach problems. And so you have to keep in your head, how do you know that you approach this problem this way instead of this way? Okay. And so I'm going to try to make that clear as we go through this stuff. There are going to be two conservation laws. The first one is conservation of linear momentum. You only use these, and you always use these in problems with collisions or explosions. So if you remember that, you always know when to use conservation of linear momentum. So if you have collisions or explosions, then you use this, and that's kind of the end of the story. And then the second conservation law we're going to use is conservation of mechanical energy. You've all had classes where you've talked about conservation of energy before. This is just conservation of energy in the case where you don't have thermal energy changes or electrical energy changes or magnetic energy changes. All you have is mechanical energy. So conservation of mechanical energy. And this one's a little trickier to figure out, a clear way to know when to use it. So we are going to always use this. So this will be useful for finding relationships between an object's location and its speed. So for example, if a problem says something about okay, this skateboard goes down this hill, how fast is it moving at the bottom of the hill? That's a relationship between the location, the bottom of the hill, and the speed that the person's going. Another hint here, is that you often won't be given information on the path that's taken. So for example, this skateboard going down a hill, you wouldn't be told anything about how many lumps there are in the hill as you go down. You wouldn't be told anything about the shape of the hill. That's another hint that conservation of energy, mechanical energy, would be the way to go on that. Okay, so all I'm going to do today is talk about conservation of linear momentum. It's simpler than conservation of mechanical energy. We'll probably get out of class a little early and we'll have plenty of time to do example problems and stuff still. So conservation of linear momentum. And this has to do with collisions. The problems I'm going to give you, I think, if I remember right, are all collisions. But this also works for explosions. I think I just don't have any problems like that.
When it comes to explosions, is it just telling you where you should be so you don't take the impact or something?
It is saying like if because of some stored up energy on the inside of an object, the object breaks into multiple pieces, what will be the velocities of the various pieces?
Oh,
Okay, so before we get into conservation of linear momentum, I have to define linear momentum. So linear momentum is this. We're going to call it lowercase p, and I actually don't know where that comes from. I assume it's Latin or something. And it's also partly just practical because we use m for a couple of other things. And the definition of the linear momentum is the object's mass times its velocity at an instant. So m is the object's mass. V is the object's velocity. And one thing to notice about this is that, well, no, forget that. I'll say that in a second. First, let me tell you the units. The units, you can get them from that equation. So it's going to be units of mass times units of length divided by units of time. And so the SI units for momentum are kilogram meters per second. And now here are a couple things to keep in mind about momentum. Yeah.
got it. Thank you.
Mm-hmm. So notice. So the first one is that linear momentum is a vector. So that means it has not just a magnitude, but a direction. And notice that the direction of the momentum is the direction of the velocity. So if an object is moving towards the back of the room, the direction of its momentum vector is toward the back of the room. Okay? Second, the magnitude of the momentum says something about how hard an object is to stop. Okay, so a butterfly moving slowly through the air is very easy to stop. A semi-truck going 60 miles an hour is a lot harder to stop, and that shows up in the magnitude of the momentum. Okay. So now that we've defined what momentum is, here is the conservation of linear momentum. So first you have to choose a collection of objects. With zero net external force acting. So I'll talk about that in a minute. And what does the external mean? That means that this collection of objects can be colliding with each other. And obviously, when these objects collide with each other, they're applying forces to each other, net force to each other. But that's allowed. What isn't allowed is for things outside of that collection of objects to be applying forces. Okay? Or, I mean, they can apply forces, but those forces have to add up to zero. And if, once you do this, then the mass of the first object times its velocity vector plus the mass of the second object times its velocity vector, and so on through all of the objects. All right, this is plus dot 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 plus m n times vn before the collision is equal to m1 times the velocity of 1 plus m2 times the velocity of 2 plus dot 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 plus m n times the velocity of n after the collision. And so we're going to do a bunch of examples, but you have to be really clear on what this requirement is. So what does this net, this zero net external force? This just means that when the objects aren't in contact with each other, so when the objects in this collection are not in contact with each other, they're moving in a straight line with a constant speed. Okay, so these objects will accelerate when they run into each other, but when they're not running into each other, they're moving with a constant speed in a straight line. What's the significance of moving in a straight line with a constant speed? What's another, what's a shorter way to say that? Constant velocity. So the velocity is not necessarily zero, but it is not changing. Okay, so this is constant velocity. And so what's another way to say constant velocity? Zero acceleration. And so if something has 0 acceleration, that means the net force is 0, remember, from Newton's second law. Okay. So if objects in this collection are not in contact with each other, but they're turning or their speed is changing, then this doesn't hold. Okay, so let me give you an example of a couple things that okay, so first, let's think of two objects rolling along a horizontal surface. Like this. Before these things collide and after they collide, are they moving in a straight line with a constant speed?
Sure.
Sure, yes, correct. So you can use conservation of linear momentum for this. Now here's a similar case. So say you have this one rolling down the ramp, this one rolling up the ramp. Would those, when they're not in contact, be moving with a constant speed in a straight line? Right, they are moving in a straight line, but the speed is changing. So in this one, you can't use conservation of linear momentum. Okay, well, let's just start with sort of the simplest example, and then we'll sort of work from there. So let's say that you have two train cars moving along a flat track. Let's say you have a 2,000 kilogram train car over here and a 4,000 over here. And let's say that the 2,000 is going 3 meters per second and the 4,000 is at rest before the collision. And let's say that after the collision, the 4,000 kilogram train car is moving to the right at 1.5 meters per second. And we want to know what's the velocity of the 2,000 kilogram car after the collision. Okay, so the first question is, before these are in contact with each other, are they moving with a constant speed in a straight line?
Yes.
Yes, so we can use conservation of linear momentum, and we know we want to because this is a collision problem. And so conservation of linear momentum says the mass of the first one times its velocity before the collision, which, I'm going to use the coordinate system we almost always use, like this. So that 3 meters per second is in the positive x direction. That's 2,000, not 3,000, sorry. plus the mass of the second one times its velocity before the collision. What's its velocity before the collision?
0.
0, yep. Is equal to the mass of the 2,000 times its velocity after the collision that we're trying to calculate. We know it's going to be moving along the x-axis some way or the other, so I'm just going to write it as v0. Plus the mass of the 4,000 times its velocity after the collision. What's its velocity after the collision?
1.5.
Yep, positive 1.5 because it's in the positive x direction, 0. And like any vector equation, now we can break this up into an x equation and a y equation. The x equation says 6,000 plus 0 is equal to 2,000 v plus 6,000. And so subtract 6,000 from both sides, and what you get is that v is equal to 0. So I just pulled those numbers out of the air, and it happened to be that if they collided in this way, the 2,000 kilogram cart would be stopped dead, and the other one would be moving. Okay? One thing you might notice about this, though, is I had to, in order to solve, to calculate in order to figure out what the velocity is of the bodies after the collision, I had to give some information about the nature of the collision. And it makes sense that I would have to if you sort of think about multiple objects with the same masses colliding with each other. Like imagine, first of all, like two pool balls, rolling those towards each other on the table and letting them collide. And you know they'll just bounce apart and go their separate ways, right? If they hit squarely. But then think about two other objects that have the same mass as those made out of Play-Doh and having those collide horizontally. Well, that collision is going to be really different, right? They're going to stick together and move one way or the other, okay? So it makes sense that you have to know something about what kind of collision it is. Are the things going to bounce? Are they going to glance off each other and one's going to go sort of off to the side and the other one will go off to the side? Are they going to stick together and move as a single object after that? Okay. So notice from this, you need to know something about the type of collision. Okay, well, in this class, we're going to do a simple type of collisions. There's no reason we couldn't do other types, but you know, we have limited time, so this is just the only one we're going to do. So in this class, we'll only do what are called inelastic collisions. And those are collisions where the objects stick together after the collision. So some of the things that like for example, give you inelastic collisions are like a person catching a ball, train cars latching together, bless you. So those are the kind of collisions that we're going to be able to do calculations for. And why does this give us enough information to solve this problem, to figure out what happens after the collision? Well, in that case, when these things stick together, you just end up with a single object after the collision that has the mass of both of those things added up, okay? And so at that point, you can calculate the velocity. You don't have to calculate separate velocities for both of them. Like, look at this equation. The difficulty here is if we didn't know that the 4,000 kilogram train car had a velocity of 1.50, we'd have two unknowns to solve for with just one equation, and we couldn't do it, okay? Now, since these things are going to stick together, we're just going to have a single velocity to calculate. Okay, so let me do an example like this. So let's say we have two carts rolling along a flat surface. And here's the little thing that's going to latch when they collide with each other. And let's say this one has a mass of 1 kilogram, and this one has a mass of 0.5 kilograms. And let's say that the 0.5 kilogram is moving this way at 5 meters per second. And the 1 kilogram, let's say, is moving this way at let's say 0.5 meters per second. And we want to know after these carts latch, what's their velocity? Okay, so one thing I want you to notice from this one is in the other one, everything was happening in the positive x direction. Since momentum is a vector, you have to take the direction into account. So this one that's moving 5 meters per second, its velocity vector is going to be -5, okay? So, all right, so what do we got? First, I mean, I think it's a good habit to always ask yourself this. Would these be moving in a straight line with a constant speed before they collide? Yes. So conservation of linear momentum says 1 kilogram times positive 0.50 plus 0.5 kilograms times the velocity of -5 is equal to the mass of the system after the collision, which is, you add up the two masses, times the velocity after the collision, which is going to be v0. And so the x equation here says 0.5 minus 2.5 is equal to 1.5 v. And so negative 2 is equal to 1.5 v. And so v is equal to negative 1.3 repeating meters per second. Well, we knew that this was the velocity vector after the collision, so now we just have to plug that in. So the velocity vector after the collision is negative 1.3 repeating 0. Or in other words, it's going to be moving this way at 1.3. Any questions about that? These problems don't have to be one-dimensional like this. You can imagine problems where you're looking down on a, like you're looking down on a surface as things move along various lines. So let's imagine that along a table, we have an object moving this way at 10 meters per second. And let's say that it makes an angle of 30 degrees with the horizontal. And let's say the mass of this object is 2 kilograms. And let's say that another object has a mass of 1 kilogram, and it's moving horizontally at 5 meters per second. And let's say a third object. So remember, this collision can include more than 2 bodies. So let's say this third one has a mass of 0.5 kilograms. And it's moving at 3 meters per second. And if all these objects stick together after they collide, I don't know what kind of objects these would be, but what's their velocity? Okay, well, that 2 kilogram object has a velocity of, so you have to figure out the components of that vector. You could use the angle of 330 degrees or negative 30, and you get 8.66 negative 5 using cosine and sine. Then the 1 kilogram object has a velocity of positive 5, 0. Then the 0.5 kilogram object has a velocity of 0, positive 3. And all this is equal to the sum of the masses, so 3.5 kilograms, times, this time we don't know what direction this is going to be moving, so I'm going to have 2 unknowns, Vx and Vy. And now we can just use the x and y equations to calculate this. The x equation says 17.32 plus 5 plus 0 is equal to 3.5 Vx. And so Vx is 6.38. And the y equation says negative 10 plus 0 plus 1.5 is equal to 3.5 Vy. So Vy is equal to negative 2.43. And so that means that after the collision, the combined velocity of this giant conglomeration of things is 6.38 for x, negative 2.43 for y. Or if you want to visualize that, go horizontal 6.38, down 2.43, and so you get a vector sort of going that way. Any questions about that? Yep. Oh. Oh yeah, I used, so here's the coordinate system. This angle is 30, so I use 330 degrees. Or negative 30 works too. Any other questions? Yeah. Okay, there's one other thing to keep in mind when you use this. We do all our calculations in planes, right? In XY planes. This conservation of linear momentum works in any plane where objects are moving in a straight line with a constant speed. Even if out of the plane that you're looking at, things are turning or speeds are changing or whatever, okay? So let's do an example like that and I'll show you what I mean and then I'll give you a chance to do the calculations. So let's say that on a horizontal surface, there's a kid standing on a skateboard. That's an alien. And somebody throws a ball to this kid with a horizontal velocity of, so the horizontal component of the velocity is, let's say, 6 meters per second. The mass of the kid is 30 kilograms. And the mass of the ball is 0.5 kilograms. How fast will the skateboard be rolling once the kid catches the ball?
Don't we need to know how fast she's going?
He's at rest right here.
Oh.
Yeah. Yes, you are right, for sure. So how fast will the skateboard roll after the kid catches the ball? Okay, well, now I said that this was going to be an example where in one plane, this doesn't meet the requirements for conservation of linear momentum, but in a different plane, it does. Okay, so think of this from the side. Before these two objects collide, the kid isn't moving at all, so that's no problem. The kid is moving with a constant velocity of 0, you know? But what about the ball? Is that changing speed or turning?
Yeah.
Both, really. So in this plane, it doesn't meet the requirements. But instead, think of this from above. So here's the kid. And here's the ball. And now, so the kid is still at rest in this view. But what about the ball? Notice that all of the acceleration of the ball is happening now out of that plane. And so to somebody observing from above, it looks like this ball is just moving in a straight line with a constant speed. Do you see that? The horizontal component of the velocity never changes. And so in this plane, the net external force is 0. And so in this view, we can do this calculation. Okay, well, take a few minutes and see if you can go through this calculation to figure out what the kid and the ball's combined velocity is going to be after he catches the ball. Okay, so before the collision, we have the kid with a mass of 30 kilograms and a velocity of 0, 0. And the ball with a mass of 0.5 kilograms and a velocity of negative 6, 0. And that's equal to the combined velocity of 30.5 times the velocity. If we assume that everything's going to keep moving along this line, I'll write this as V0. And so the x equation says 0 minus 3 is equal to 30.5 v. And so v is equal to 0.098. This is negative 0.098 meters per second. And so the velocity vector is negative 0.0980. Anybody have any questions about that? Okay, well, that's really all there is to these. let's stop there and we'll just start again next week with conservation of mechanical energy. Remember, Monday is Veterans Day, so there's no school Monday. And okay, have a good weekend.